Hi there. My name is Dr. David Hall, and I'm going to give you a quick outline of the latest Robotic Vision Challenge from the Australian Centre for Robotic Vision, now in association with the Queensland University of Technology Centre for Robotics. This new Robotic Vision Challenge is a Semantic Scene Understanding Challenge. Alright, before we get much further, I would like to acknowledge all the members of our fantastic team that helped get this project going. We've got Nico Sunderhoff, Faraz Tayoub, myself, Hayoung Zhang, Ben Talbot, Suman Buster, and Rowan Smith. I'd also like to acknowledge the contributions of some of our team alumni, John Skinner, who is heavily consulted with everything regarding simulation, and Gavin Sundry, who did a lot of the early work on our benchmark platform that I'll talk about later. So our aim here is to try and create an indoor robotics challenge that is accessible to non-robotics computer vision and machine learning researchers, wherein a robot must learn to understand what objects exist within their environment, a very important problem within indoor robotics research. The goal really being to try and take challenges of the sort that are familiar to computer vision and machine learning communities, but apply them to more robotic vision focused problems. Our challenges being the way to bridge the gap between these two communities and have us all walk hand in hand together into the future. So there are several parts to the Scene Understanding Challenge that I'll try and get into within this talk. The first is outlining the two new challenging tasks that we have created. The second is talk about the new evaluation measures that we have created for evaluating performance. The next is the fact that we actually provide 3 different challenge difficulty levels within the Scene Understanding Challenge. And the final is the big one, which is our new benchbot simulation framework, which is able to abstract robot control and enable easy sim to real transfer. This is the tool that we want to use to enable machine learning and computer vision researchers to start focusing on these robotic vision style problems. So let's get to talking about our Scene Understanding Challenge itself. As mentioned before, we have 2 challenging tasks. We have the Semantic Slam task and a Scene Change Detection task. With the Semantic Slam task, the goal is to use a robotic agent to explore an environment and produce an object map, like you see at the bottom, of all objects of interest within the environment. The map that you produce will provide the 3D cuboid locations of all objects of interest, things like tables, chairs, etc. It is your goal to explore the entire environment, produce this map, and then you will be evaluated using our new evaluation measures that we'll get to in a bit. Our Scene Change Detection task works very much in the same way. However, now you must explore an environment twice. Between 2 separate traversals, there may be some lighting variations, like you see here, but more importantly, there will be some objects in the environment which have been removed, such as this chair, and there will be other objects in the environment which have been added, such as this monitor. The goal of the Scene Change Detection task is to create a 3D object map, but more importantly, to map out which objects have been removed and which ones have been added. This will again be evaluated using one of our new evaluation measures that, well, let's talk about now. So the evaluation measure that we have created for our Scene Understanding Challenge is the Object Map Quality, or OMQ. Now, this is a new measure that we created to try and evaluate the semantic object maps, like you see on the screen, which are the expected output from the challenge. Now, for our purposes, we'll quickly define a semantic object map as a series of object proposals, which themselves are defined using axis-aligned 3D cuboids and a label probability distribution describing all the different confidences that the proposal has as to what class it might be. Now, this is very heavily based on the probability-based detection quality, or PDQ, evaluation measure that we had created for the probabilistic object detection challenge. If you are still confused about OMQ by the end of this, first of all, I'm very sorry. And second of all, I recommend you check out the implementation of PDQ as defined in the paper, or I've done a quick video about that somewhere on YouTube. Just look it up. All right, so starting off with OMQ, you are going to begin by calculating a quality score between all proposals in your map and all ground truth objects that you're trying to describe. The quality score here is made up of a spatial quality, which is just the 3D IOU score between the proposal and the ground truth object, and a label quality score, which is just the confidence that you gave for the actual class of the object you're trying to describe. So You're going to get a score for every proposal in your map and every ground truth object that you were trying to describe. And then we are going to simply assign all object proposals to ground truth objects. We're going to do this optimally, and it'll leave us with a bunch of true positives in big air quotes, where there is some non-zero quality match between the proposed object and the ground truth object, a series of false positives, which are proposed objects with absolutely no quality match between any ground truth object, and false negatives, where there is no match for a ground truth object to anything in the proposed map. And your final score is simply an average of the assigned qualities over the number of, in quotes, true positives, false negatives, and a weighted false positive score. What I mean by the weighted false positive score is that every false positive from your map is weighted by the label confidence that you gave maximally, aka the more confident you were that it was something, the more you will be penalized for being wrong. Okay, now OMQ is going to work basically the same across semantic slam and scene change detection tasks. However, it's going to be a little bit different for scene change detection just because of the different sort of map that we're trying to create. So that map, as seen here, now not only has to care about what class something is, but also whether or not an object has been removed or added. For this purpose, the object proposals will now have a state probability distribution, which has the confidence that an object was removed, added, or stayed the same. How this affects OMQ is simply that the state probability now equally contributes to that pairwise quality that we talked about at the beginning of OMQ. So now instead of just caring about the spatial and label qualities, we also now have a state quality. And that false positives are now weighted by the label and state probability. So now if you are, the worst case scenario is being very confident that an object is of a certain class and very confident that it was removed or added. Regardless of the task, we provide 3 challenge difficulty levels, each one corresponding to a different amount of abstraction of the robotic system. This enables people without as much robotics experience to still participate in the challenge. In passive mode, there is no need to directly control the robot at all, as it will move between a set of predefined nodes with a move next command. This is completely consistent between runs, and at each node you are provided with your normal sensory information, cameras, LiDAR, etc., as well as the ground truth pose of the robot. All this means is you do not need to actively explore or perform localization for this difficulty level. In the second difficulty level, you will need to explore, as you now have direct control over the robot's actions with our abstracted API, allowing you to move a distance or move at a certain angle without any hassle. However, after each action, we will still provide the ground truth pose information, so you do not need to worry about localization. In the hardest difficulty level, you are no longer provided that ground truth pose information. Instead, you will need to estimate your pose as you try and explore the environment, meaning you now need to explore actively, avoid obstacles, and make sure that you are self-localizing accurately. It is this difficulty level where, if you are successful, we will allow you to use your code on a real robotic platform. But now that we've started talking about real robotic systems, I can finally talk about how we get it all to work. The nuts and bolts of the system, I get to talk about BenchBot. BenchBot is a collection of software packages that we've developed which allow control of both real and simulated robots using a very simple Python API. Our philosophy behind BenchBot is a pretty simple one. Robotics is hard. There's a lot of complexity to even get the most basic thing working. If we can simplify that, we can start working on some really high-level problems. Sim-to-real experiments should require no code changes whatsoever, and more importantly, it should be simple to use for even non-robotics researchers. Popping the hood a bit, let's have a look at BenchBot itself. How it should work for you is that you simply submit your Dockerized version of your code to BenchBot and it will take care of everything else. The BenchBot API will enable you to have access to those nice simplified control commands. The BenchBot supervisor will instruct what information should and shouldn't be passed to the API and to ROS. And then through ROS, you'll control our BenchBot platforms. If it is a robotic platform, it is one that we have set up to accommodate these nice simplified benchbot commands, or it will be the simulator, in our case IsaacSim, which has also been set up to accommodate our nice simplistic benchbot API commands. After the entire test is done, you will get your evaluation results at the end for the challenge that you were trying to participate in. But even that level of complexity, you shouldn't need to worry about. All you should need to worry about is programming that nice high-level behavior, checking into benchbot, and knowing that you will get meaningful results out of the system. We've tried to make the benchbot system as simple to use as possible, both in terms of the abstracted API with which you control the robot, but also the very scripts that help you get started. We've tried to make it as easy to use as 1, 2, 3. Script 1, benchbot install. This is where you get yourself started. It will step you through the entire installation process, any known errors it will offer a solution, and it's also the place that you go to handle any updates of the system. If any individual package in your benchbot framework is behind, benchbot install is what you will need to run to get everything up to the current level. Script 2 is benchbot run. We'll get into this one a bit more when I show a short demo later, but it is where you will go to set up your experiment scenario. Benchbot run lets you decide what task you're trying to perform, what difficulty levels you want to perform it at, and in what simulated environment would you like to give it a shot. Script 3 is benchbot submit. Again, we'll go into this a bit more in the demo, but it is where you will finally submit your solution. Once you've got your robot behavior and you're ready to test it out, it is the script that you will run. You can perform your tests either in native mode or a containerized mode, and you can also set it up to automatically perform evaluation once you're done. This is regardless of what task you're trying to perform. Now, as well as these three, we also have another script, which is more for when you finally have your solution and you want to test as many times as possible. And this is an easy batch running script, benchbot batch. It will allow you to run the same submission for multiple scenarios. So if you have one solution and you want to test it across multiple environments, benchbot batch is what you will run. Again, we'll get into this a bit more in the demo. Speaking of which, and like that, I am on my Ubuntu machine, and I can show you some of the basic functionality of benchbot. This is by no means going to be exhaustive. For more in-depth information on the benchbot system, I'd highly recommend you check out our GitHub page. In particular, we made up a nice tutorial that will step you through making up your own benchbot agent, and it'll also go through the scripts that I'm going to run here. So let's get started with the first of our easy 1, 2, 3 scripts, the benchbot install script. So here you'll notice that I'm in a virtual environment. This will be installing some Python packages, so make sure that you are in a virtual environment or a Python environment where you're happy with that taking place. You'll see here that it does a whole bunch of checks, making sure that you've got the minimum requirements in order for us to install things. More information on the full installation prerequisites you can find on the GitHub page. This entire process should be pretty quick for me, as everything is already installed and should be up to date, though it is still slightly slower than others. If you are using a spinning disk, you will be operating a fair bit slower than anyone who's using a solid-state drive, so you'll be in the same boat as me. Okay, so it's created our Docker image, so it was already set up for me. It's checked that all of our repositories are up to date, and we are now ready to go. So let's try and actually run something with benchbot run, our second of our simple scripts. Let's first have a look at what it's able to do for us. So with benchbot run, we are going to be able to define the environment and the task that we are trying to perform. This is basically setting up what experiment would you like to try and perform, and it is the main thing we're going to really need to check for. So let's just clear that and benchbot run and have a look at what environments we have available. So this is the full set of environments we have. So every environment has a name and then a number for what variation of that environment we are looking at the time. So that number is particularly important for scene change detection. And for your testing on your own machine, you are going to be concerned with house and mini room, as those are our develop environments where we provide you with ground truth object maps, whereas apartment, company, and office are used for the official challenge. And if we just list the tasks, we see what we would be expecting. We have 2 tasks, Semantic Slam and SCD, and we have our different control mode and localization mode to define the difficulty level. So passive ground truth was the simplest, active ground truth was the next, and then finally active dead reckoning is the most challenging version of things. So as you're going to see in a second, you run a benchbot run task with defining what the task is, what control mode we have, and what localization mode we're using. In fact, let's give that a go now. So, just for an example, let us go with the task of Semantic Slam with active mode and ground truth localization. So this is the middle level difficulty one. And we will run in environment mini room 1. Okay, now at the moment I have set things up so that it is going to check the entire system to make sure that everything is up to date. If you are certain you're up to date, or because you've recently installed, you've recently updated, or you're just really paying attention to all of our communication channels, you can pretty safely run a -F flag here to skip this step. If you're not sure whether you're up to date, I recommend just letting this do its check so that you can make sure that you are using the most up-to-date version of our software, our environments, of everything. Okay, this is going to start up a little scenario here. We see that everything is set up correctly. We have, because we're in active mode, our actions of move distance, move angle. We're in mini room, and these are the sort of observations we're going to be able to get. Okay, sweet. We have our robot in our nice small apartment area, and now we actually need to use it for something, which means it's time to use our third bit of code, benchbot submit. So there's a bunch of options here. We're only going to be caring mostly about the top 4 here. So containerized and native define what mode you're going to be running in. Native mode is running on your own machine. Containerized mode means running using a Docker file. Submission just bundles everything up to be able to be used on an external platform. So if you are lucky enough to have your code applied to a real robotics platform, this is what you're going to be using. We can evaluate our results during the run and save our final object map to a precise location. Okay, let's clear that up and actually run something. So let's run in native mode our example of hello active, and this is just going to give us direct control over the robot manually, so I can show you the sort of actions you're going to be able to do and observations you're going to be able to get. So here's a little visualize that we've made for hello active. You can use it yourself if you're wanting to for your own debugging of the system. And you can see here that we have our RGB image, our depth image, we see the laser that we're getting for the robot, and the pose information for the robot. And we are able to move the robot by a given angle. We are able to move by an angle as small as 1 degree and still get our data. And we can move forwards and backwards. And the robot will always move to within 1 centimeter and 1 degree of the desired location, so making it highly repeatable. Okay, so that's the movement, and you can see that everything updates after every action that is performed. So after every action, you get a new set of observations. Right, let's close that up. But wait, there was something else I wanted to show you. But rather than having to go through the entire benchbot run system again, if I just resubmit what I did before, it is going to notice that the state is dirty and reset everything so that we are starting the same experiment but from afresh. Meanwhile, benchbot run is just running as it always had been. I haven't had to do anything, no jiggery pokery there. It's still just the single benchbot run command. Okay, and the last thing that I will show you with benchbot submit here is that if you crash your robot, your scenario ends. You are not allowed to continuously crash your robot no matter how much fun it is. It's not supposed to be the goal of the challenge. Alright, so let's end that experiment setup and actually get to something with some results and have a look at evaluation. So let us now clear all that. Let us run a benchbot, run a new task. Let us go with task semantic slam, but in passive mode this time with ground truth. And let's switch up the environment to mini room 5. Sweet, and we will let that run. Okay. Now let us run the new solution. Now we're going to do benchbot submit again, but we are now going to put the -e flag on to automatically evaluate, and we are going to save our results in demo results.json. And when I say results here, I'm meaning the final 3D object map. So we're going to save that there so we can evaluate it later if we so wish. Alright, and we'll put ourselves into native mode, and we will run our example of semantic slam attempt. All of these examples will be available to you. Alright, getting ourselves all good. Alright, now as this is a passive mode, it is not doing anything smart with its navigation here. It is simply moving to a set of predefined nodes. Okay, and we're done, and we see here our evaluation performance. So we see our OMQ score, the overall score that we should get, and we also get a bunch of submetrics to let us know how good we are at determining where things are, what they are, overall combination of the two, etc. And, let us clear this, we should be able to get our results just by simply doing benchbot eval demo results.json. So we saved our file to demo results.json, and we can get our evaluation results yet again. Alright, let's clear everything that we've got now, and let's close benchbot run, because we still have one final script to show off, and that is benchbot batch. So let's just clear that up. Benchbot batch. I'm not going to go through the help file for this one. I'll just save you some time and let you know that it's got a lot of the same flags as benchbot run and benchbot submit combined, because it's going to do a bit of both. So let's set our task as semantic slam passive with ground truth, and then we're going to have to set our environments. Now this is where benchbot batch is different from benchbot run and benchbot submit, is we can have multiple environments. So if I wanted to, I could go mini room 1, mini room 2, mini room 3, etc., etc. But instead, what I'm going to do is the other way that you can use benchbot batch, and have a file which defines all of the environments that you want to use. So let's just use m's file, and we are going to use one of the pre-provided ones that we give you. So benchbot batches, develop semantic slam passive with ground truth. So use that. We will score our results, We will run in native mode, and we will use the solution of examples semantics lamp attempt, semantics lamp attempt. So this will now go through all of the environments in the batch file. It will give us a score at the end. We are running natively, and we are using the solution semantics lamp attempt for all of the different environments. The environments being mini room 1, mini room 3, house 1, house 3. So now we just let that run. Alright, and that's it. As you see, it's been through all the environments. You can get an individual environment score, so you can see how well you did at mini room 1, mini room 3, house 1, house 3, and what your final score is across all of the environments. And with that, we have pretty much been through all of the bare bones basics of BenchBot. You can check out the code itself to see all of the fun little tools we have in Python to help you get going. The agent class, which you use to abstract to any sort of agent that you want to do, just filling in these 3 functions and you're good to go. And for those of you who are a bit confused by that and prefer things a bit more of the AI gym way, we give examples of that as well. For more information, I would definitely recommend you check out the BenchBot GitHub. We have links to all the individual parts of the BenchBot software stack. And we have our cool tutorial that will step you through absolutely everything in a lot more detail than what I have done. So, with that out of the way, let's get back to the main talk. So, in summary, we are providing a new scene understanding challenge. We have 2 new tasks with 3 different difficulty levels. We have introduced our new BenchBot framework, which helps all the magic happen. It abstracts complex robotic tasks to focus on high-level problems. It provides easy sim-to-real transfer, and, importantly, it's really easy to use. If you do choose to participate, there are prizes to be won. High-performing participants have a chance to win part of $2,500 and get a chance to test their code on the Real Robotics platform. If you're checking out the important dates for this challenge, on the 2nd of September our final submissions are due, and on the 2nd of October the winners will be announced. On behalf of everyone in our project team, I'd like to thank you very much for listening, and we really hope to see you soon in the Scene Understanding Challenge. If you're looking for more information, if you want to participate in the challenge, if you want to contact the team, if you want to chat with us on our Slack workspace, then here's all the information you should possibly need. Thank you very much again for listening. Take care.